Hey guys, welcome back. Today's video is don't learn Scikit-learn. So don't get intimidated. Basically, it means that you should not learn the Scikit-learn in the way it is supposed to be for any other library. It turns out that Scikit-learn is the most popular ML library which is being used in industry. But as a beginner, you will try to learn all the modules and everything. But it turns out you don't need that. You just need to understand few fundamental principles which I will be explaining in this video to get started. So let's start today's session. So before starting, let's clear up our agenda. First of all, our agenda is very simple. We are first going to learn about the Scikit-learn API structure. Then we will understand the Scikit-learn design principles. Then the three fundamental types of Sklearn objects, which is pretty important. After that, different modules we will see, say data API, model API, and what all the things that are required in all these. And then I will be giving you practical advice that will help you to enhance your learning further. So don't worry, everything will be covered in detail. Let's start now. So the best fact about the Scikit-learn API structure is that it is a very organized framework. In general, Scikit-learn is organized around a generic machine learning framework which typically includes loading our data, preparing our data, like removing null values and outliers and everything, pre-processing our data for training our model, then model selection, whichever model you want to use, then evaluation of model. Basically, once you train your model, you need to evaluate it in certain ways. So that's what you can do with this. And after that, inspecting your model and repeating all these things again. So all these are provided by Scikit-learn. And the way it is provided is using the pipelines, which combines all these. So different components map to a specific state. For data part, we have data loading, preparation, and processing. Then for model, we have our training and loss function. Once we have our model, we need to optimize its parameters. For that, we have model selection, and after that, we need to have evaluation. So we have our model inspection. These are the steps which are typically used. Don't worry, we will be looking at everything in the practical way very soon. So bear with. Let's now look at the Sklearn design principle. How it helps us to do things very easily. First one is consistency. So all APIs share a simple and consistent interface. For example, all estimators have this fit method for your training. So there are multiple objects in Scikit-learn, and one such object is estimator. For all these estimator, you will have this fit method. So by default, method is nothing but a function. Okay. After that, there is standard data representation. So suppose you have different type of data files like JSON, CSV, sparse, anything, but under the hood, the Scikit-learn leverages NumPy and SciPy sparse matrices instead of custom classes. So any type of data, you need to first convert it to your NumPy array or SciPy sparse matrices so that it can be used to train our model. That's what we do in our data processing step. Okay. After that, composability is there. So we have this building blocks like transformers, estimators, and predictors, which can be combined into multiple complex pipelines. We will look into pipelines later on, but for now, you just understand that we can plug and play things in very good way using Scikit-learn. That's all. Okay. And after that, we have our sensible default. So sensible default means things that you don't need to specify, but is present there in a very sensible way. And by sensible, I mean the values for those particular parameters are logical and mathematically proved. Okay. So default parameter values can help you quickly build up your baseline models. So baseline models means the fundamental, the most simplest of models which we will be building in our ML project. Okay. Now let's look at different Scikit-learn objects. And this is the most fundamental thing that you need to understand which module to use where. Okay. So Scikit-learn actually provides us three types of objects. First one is the transformer. So anything which can transform our data set so that we can easily manipulate things is called a transformer. By default, a transformer will have this transform method, fit method, and this fit underscore transform method. So fit actually learns the parameter values of the whatever data. For example, say we have our x1 is equal to x2 plus x3, and these x1, x2, x3 are nothing but the features. So what all parameters will this value take so that our x1 will get the desired value which is in our data? So that kind of relationship, first it understands, then it applies this transformation method, which will allow the data to get transformed and get returned in a new feature, say x1x or whatever in place, so that you can work on it. And by default, fit underscore transform does both the steps in one way, and it is the most standard way in which you should transform your data set. Okay. After that, second is estimators. So estimators by name, it means it can estimate parameters. So here we were using features which were part of data, but in machine learning models we have multiple parameters. Say a learning rate, we have our bias, we have our intercept. So all these things needs to be estimated. So same thing we can do here, because it says train machine learning model, and the method which is allows is fit predict and fit predict. So wherever you can use this fit predict and fit underscore predict, it means that you are using an estimator as a base class. Okay. And again, this fit does the same thing which is done here, but instead of using these particular values our data, it uses the parameters which is need to learn, and predict actually predicts that using those particular parameters. Now estimators and predictors work hand in hand, but there are few dissimilarities also. So predictors actually help you to predict on your data, and it consists of this predict method, score method, and predict probability method for classification or regression algorithms. And again, this predicts the data. This gives us the score, that is the actual data that you already have and the predicted data. What is the difference in those? And predict probability is nothing but gives the confidence also. Say it's 0.89. So that means it is 89% confident that this particular data will belong to this class, or this value will be under this particular probability range. I know there are a lot of things which I am talking about and it may not make sense, but as we go along, it will help you understand. But just understand that you need to understand these three things: transformers, estimators, and predictors. I would highly recommend that you refer to other resources as well to understand this particular thing. Okay. After that, we have our Scikit-learn module data API. So in data API, it is all related to data. Whatever data you have, you can use those to do multiple things. First one comes as Sklearn.dataset. So whenever you are learning machine learning, you need to first understand most of the things on your toy dataset, and by default toy dataset is implemented in Sklearn.datasets API. You can learn more at this particular URL which I will be providing later on, and you have this functionality of loading your custom data and reference data set as well. We will look into these in later videos, but for now just understand this. Next, once you have loaded your data, you need to pre-process your data. So pre-processing means scaling your data, centering your data, normalizing your data, binarization of data, right? So all these things you need to do in order to make your data workable or easy to understand. Again, you can learn more at this particular URL which I will be providing later. After that, there are a lot of missing values most of the time, so you need to handle missing values. The Sklearn.impute API to handle such values. For example, if we use simple imputer, we can impute our data with mean, median, mode, and whatever statistics we want, and there are much more than that. Again, you can learn more at this particular URL which I will be providing later on. After that, we have our feature selection, because you already have your imputed data, you have processed your data, but now it turns out that most of the features are redundant. As I showed you earlier before this slide, that x1 was the combination of x1 plus x2. So we can drop off that x1, right? So in such a case, we can use feature selection module or API which has multiple functionalities inbuilt so that you can select your best features. Again, you can learn more at this particular URL. Okay. After that, once you have your data API, now comes the model building. Okay. Everything which I will be covering here will be part of model building or whatever we will use for our model. And this is the 20% of the work that you will be doing only. Okay. Most of the time will be spent in the previous section only. We know that our machine learning has a supervised and unsupervised learning paradigm. So for supervised learning, say regression, we have linear, rich, lasso, which comes under the linear underscore model API. And we have our decision trees, random forest, and everything like that in scikit-learn.tree. So tree-based model, and linear models. Okay. Now, on the other hand, we have our supervised learning as classification. So classification means to classify. We have logistic regression, support vector machine, decision tree, k-nearest neighbor, classifications, multi-class and multi-output classification, multi-output regression, and all these are implemented in a separate class. Say for support vector machines, we have many different types of support vector machines. All are implemented in sklearn.svm. Tree-based models that are combined in sklearn.tree and sklearn.ensemble. Clustering algorithm, we have sklearn.neighbors for it. Naive Bayes, which is again kind of a classification algorithm. It is implemented as separate class of naive Bayes because there are multiple ways and you can implement naive Bayes. After that, multi-class and multi-output classification. What is that? Sklearn.multiclass. This is kind of a pre-processing also, in which you can use your data which has a single class to convert into multi-class. Don't get into nitty-gritty details of these models. Just understand where to use what. Once you have your model, now what you will do. So for that, we have our model evaluation API, which comes under sklearn.metrics, which provides us classification metric, regression metric, and clustering metrics. So all metrics are combined in this particular metrics class. You can understand that for using any particular metric, you can use this sklearn.metrics. Similarly for dataset and for clusters also, right? Now, once you have your model evaluation API, there are multiple models which we want to select, right? So for that, we have this our cross-validation, hyperparameter tuning, learning curve plotting. All these are present in model_selection API. That is the name of the module itself. Okay. So every time you need to import anything related to model selection, you need to use the model_selection and import from that. After that, once you have your model, now it's time to understand whether our model learned is good or bad. For that, we have inspecting our trained model using sklearn.inspection API. So these are some fundamental classes that you need to understand in order to get started with implementing things and later on. So before moving on to any practical part, I would like to share practical advice with you. First of all, remember the high level modules and design principles in mind, like whatever I have shown you in previous few slides. Also, you should remember that learning ML is not about how you will implement it. It's not about it. It's about what parameter to use where, with which model, and when to use it. So these are called 4 Ws. These are invented terms, by the way. So these are the few things that you need to understand. After that, we have our documentation. All the links that I have provided can be used for the documentation. Again, say if you are using some code and you are not understanding, you just need to import that particular thing. So for here, for example, I am using logistic regression from sklearn.linear model, and I am adding this question mark in front of the module name itself, and it will access the documentation for you. So these are few fundamental things that you need to understand. Okay, so we have understood most of the things, but now let's implement all those things to see how it all gets combined and makes your work life very simple. We will be taking a simple use case. So guys, welcome back to this practical section where we will be going through a sample problem statement, and I will be explaining you all the concepts that we have covered in theory using code. I hope that you will understand a thing or two, and if you don't understand, don't worry about it. Just go through whatever I am going to explain you, and we will be covering everything extensively in later videos. So let's begin now. So let's begin by understanding our problem statement. So imagine that you're working as a data scientist with your task being creating a predictive model that can classify a set of plant species based on certain measurements. So the aim of the project involves various stages in typical machine learning pipeline, where each stage utilizes a different Scikit-learn API component, and we will be covering everything step by step. So first step is loading our data, because without data, how can we do that? And for this, I am using the IRIS dataset, which contains information about different flower species, and our goal is to build a model that can predict the species or the target based on the sepal and petal dimension, which can be thought as the features. So as you know that we can load our sample dataset from dataset API. So that's what we are going to do now. We are going to load IRIS dataset from Sklearn using dataset API. For that, the code is from sklearn.datasets import load underscore. Okay, so this will simply load the iris data set, but we need to store those things, right? So for that, I'm going to do data, because we are taking our data. So data is equal to load underscore iris. And the thing that we have already imported is nothing but a function which will load our iris data set from the base repository. And after that, we are going to split our data set into training and test data. For that, we are going to do s comma y is equal to data.data comma data.target. Don't get details, just understand that this particular data.data will get stored in our x, and this data.target will get stored in our y. Now, if I select it and run it, it will take a couple of minutes because we have not yet been connected with the hosted environment. But once we connect, can see that we will have our data. X, you will see that have our data, right? And if I do Y, you will see that have our, and these are 0, 1, and so this is a multi-class classification problem, which means that we have multiple classes and each of the class will only belong to one particular set. Well, so now once we have this, next step is pre-processing our data. And by pre-processing, for here, I am going to do a simple scaling operation, but you can also do normalization and transmission. Don't worry about all these details. For optimal model performance, we are going to all these steps. And here, we will use the standard scaler function, which will standardize our feature set. That means making the features at same scale. And we will make sure that each feature has a mean of 0 and a standard deviation of 1, kind of a central limit theorem. And this helps the algorithm to interpret feature importance uniformly. So each will be given same importance. So for that, we are using from Sklearn.processing, import standard scaler. And then we are creating a scalar object by default, which it means that we are taking this standard scalar implementation in the Scikit-learn API and taking a copy of that so that it covers all the features and everything. The standard scalar is a class and scalar is nothing but an inherited object which will have all the properties of standard scale. And then we are creating a new variable xScale and we are fitting our data as scalar.fit underscore transform. So by default, it will just fit our data, that it will learn whatever the essential things are and then it will do the transformation. Let me run it again and you will see what I mean once I print this. Okay. Now, one thing to understand is that we will not be doing this on our y, that is our. So you can see that these values have become very small so that machine learning models can interpret. And I can say that it's very small because you can see here it is e minus 0, 1, right? So this is kind of thing that I was talking about. Now, unfortunately, this data doesn't have any value, but most of the data set will handle that. First, we will introduce some missing values. Then we will impute it using the simple imputer. So first of all, we create the missing values. So for that, I will import numpy np and I will create nan values. For that, I will be doing xScale 0, 0. That means 0 row, 0 column. That means at the very beginning, np nan. And after that, if I do this xScale, you will see what we have, right? You can see that my first value is actually nan. So in most of the data set, you will have these steps, but Sklearn.impute provides us various methodology that can use to fill this missing value. And it is very important because model will not understand this nan. Okay, so here we will import our imputer from Sklearn.impute, import symbol imputer. Then we will again create a object with specifying the strategy as mean and applying this imputer on imputer.fit transformed xScale. And this what it will do is it will take the entire mean of the first column and impute the value. That means put the value at the position of nan that we have seen earlier. Okay, and if I run it now, you can see that my x imputed is nothing but the first value will now not have this nan thing, right? So we got this value. That's the imputed mean. Okay, now these two have already done, but now it turns that if you have multiple features, how you will find which are the most important features. So for that, we have this feature selection part, and here we will try to reduce the dimensionality of our data. You select k-based. Obviously, you can also use principal component analysis, that is PCA, or other techniques are also available in this particular feature selection API. So for that, I am going to import select k-based from scalar.feature selection. Basic simple import from scalar.feature selection select k-based. And now the same thing will be there, that we will be first creating our object, and we will say setting that need only features which are the most relevant and captures the most. Okay, so first of all, like this, then selector, and selector is basically the object that we are going to use, and we will be using selector, not select k best, and this is a very standard practice, so make sure that you follow that. And now for fitting our model, we will selector.fit x imputed comma y. Why this? Because we want our relationship to be identified. For that, we should have this y is equal to mx plus c relation, and for that you need to have this target label as well. Now this, and you can see that select k best. Okay, now if we transform our data, we will do this x selected and selector dot transform. If I run this, you will get the selected. And now if I want to get the feature names, I will do select feature names, and here I am using a list transformation for this. Here we have data.feature name for I in selector.get. So get support will basically return the indices of the column names, say 0, 1, 2, or 3, and then we are using those indices values to get this feature names column, which is again the property of this data or the bunch object. And I try to print select feature name. You will see that we have these features which are the most relevant one, petal and CM and widths. Okay, so this is a demo on data set, so don't worry about all those details and integrity things that are being done here. So now we have our multiple output case, and unfortunately our data is a single output, but it may be like we have a flower with 2 labels, and for that we use our multi-output classifier. And to demonstrate it, we are going to change our data set so that it works. So first of all, we need to import the multi-output from the classification model. So for that, we will do from sklearn.multi-output import multi-output classifier, and from sklearn.linear model import logistic regression. And the reason we are using logistic regression is because we need to have a estimator for this multi-out classifier to work. Okay, so first let me import that. Now, like any other object, we need to create an instance of multi-out classifier. So for that, we will be defining model is equal to multi-output classifier, and this estimator will be defined as logistic regression dot fit x selected comma y. And x selected is nothing but the feature columns, and y is the labels. Okay, and by default, if you run this now, you will see you have this y must have at least 2 dimensions for multi-output regression, but has only 1. The reason is that it is a single dimensional array. But if you have multiple output, it should be multiple, right? So to handle this, we are going to change our labels in a specific way. And for that, what I'm going to do is I'm creating a separate copy of the y in the same frame matrix. So for that, we are going to use np.column underscore stack, which will kind of stack a new column y comma y. If I do this and I try to train my model, you can see that it will work. And here we have our estimator as logistic regression, and this entire thing that you are seeing, it is called a pipeline. So whatever things are going to happen, it will be displaying here. And again, we have our pipeline class as well, but we are not going to cover it here. We will be covering it later in the detailed video. Okay, so once we have our model itself, now we can get the output. So output will be model.predict x selected, and it will predict our data. And you can see that it is doing very good in first glance, right? It has 1, 1, 2, 2, 2, 2. But this is not a good model. It is an overfit model. It has just learned the training data very well. Now, it may happen that you have certain hidden patterns in your data that can be uncovered through clustering analysis. Clustering analysis is very important in few unsupervised learning tasks. Though this is a supervised learning task, we convert it into unsupervised learning task. So we will use agglomerative clustering to cluster data into different groups based on the similarity of features. And although it is an unsupervised technique, clustering can reveal hidden structure in data. So let's look at how to do that. Though it is not very important here. First of all, we will use the cluster API to import this agglomerative clustering method. Okay. So once we have this class. Now we need to initiate our object. So for that, we need to create our cluster, agglomerative clustering, and cluster is equal to 3.selected. And now once you have this, you can run it and you will get your cluster labels. You can see that this all is kind of very close to each other based on the feature similarity of sepal width, petal width, while here you can see a disk balance 0, 2, 0, 2. So these are kind of mixed clusters. So we need to somehow handle those also in our dataset. Now after that, we need to select our model and train our model. And here also model underscore selection will help. But there are a lot of steps involved in this, and there are multiple things that you need to understand in this particular API. So for classification task, we will choose our logistic regression as our base model. But logistic regression also has this hyperparameters which are not learned by the model itself, but by the data. Okay, so for that, we need to provide it from the outside. So obviously, we are not very good as computers, so we need to handle it somehow. So for that, we will use grid search CV or random search CV in our use case, which will create an exhaustive search of all the parameters to find the best hyperparameters so that our model is optimized. And then we will do a cross validation so that we get same type of output on multiple dataset. Obviously, we can't create the dataset again. So we need to somehow manipulate our data so that only one portion of our data is for testing and the remaining n-1 portion is for training. Okay. So this, it can be achieved using CV or cross validation, and to get the scores around it, we need cross value scores. Here you will see where Sklearn truly shines, because here you can see that we have 3 parameters, but it all comes from this model selection API. So we have Sklearn model selection, import grid search CV, cross validation score, and train test split. This is just to split our data into training and test set. Then we will load our logistic regression from the Sklearn.linear_model, import logistic regression. I do this, it is done. Now we will create our train test split, which is kind of very standard, and it simply means that you are creating a set of training data and a testing data and keeping the testing data separate so that you will not overfit your model. Here we have xtrain, xtest, ytrain, ytest is equal to train underscore test underscore split, x selected, y, test size equal to 2 and random is equal to 4. So just understand this, xtrain and ytrain are nothing but our training features and training labels respectively. Similarly, xtest and ytest are nothing but testing features and testing labels respectively. And we are taking a 20% split. That means 80% of the data will actually go for the training, and the remaining 20% will be for our testing. Okay, so keep that in mind. And random is 42 is nothing but a seed so that you get the same results multiple times. Now we need to define our model so that we can later use it, because our grid search CV will require an estimator and logistic regression will act as the estimator here. Okay, now we will create a parameter. This is pretty important because this is how you will be implementing grid search CV in the machine learning context. Okay, so first of all, you will create a parameter grid. So parameter grid is nothing but a dictionary with key value pairs, where key is the name of the parameter of whatever model you are using. For logistic regression, we have this C, which is kind of a regularization parameter there, and then we have the values in which we have to search. But one thing that you need to understand here is that these parameter values, don't put it as you wish. You need to make sure that you are using the right set of values, else this will cause an error. Now we will create our grid search object, and for that I am going to use grid underscore search, grid search CV, and now we are passing our estimator and then param grid, and then we are saying that we need 5 cross validation. Then we will fit our model, that is kind of train our model. So grid search dot fit xtrain and ytrain. Then we are going to get the model. So for best model, we are using the grid search member variable called best underscore estimator, which will be stored in best model and which will be used later on. So let me run it, and we have got our best model. It seems print the best model. You can see that we have our logistic regression as C has this value of 0.1, which is performing very good, it says, right? So how good it is? It is a very common question. So we need to evaluate your model performance. And for that, again, we have our metrics module.sq, where we can use this accuracy, precision, recall, F1 score. And these metrics will provide us insight into the model performance or whether it is balanced across all classes or not. So for that, we will first need to import the scoring function from the metrics module. So from sklearn.metrics, import accuracy score, precision score, recall score, and F1 score. Just imported it. Now, this is very important. These all will not work in normal way. you need your predicted data as well as your actual data to predict it. And by data, I mean the labels. So how you can do that? So we have already trained our model earlier, right? So we can use this best underscore model, which will be taking our best model and then dot predict method as it is an predictor and estimator. And then we are passing the X test. Now this, if you see, our y-pred will have the prediction values. Now we are using this y-pred and the y-actual to check how many are wrong and how many are right. For that, we are going to print multiple scoring function. And if you remember, when we splitted our data earlier, we had this y-train and y-test. So we are going to use y-test and we predicted on x-test. So we already have this data, right? And now we are going to print multiple evaluation metrics. And again, this is kind of optional. Again, here, if you don't understand, we are just going to do a print and then we are using all the methods that we imported earlier, passing it our actual data and the predicted data. Now let's check how it is performing. The main aim is to look at the F1 score. So F1 score, if you see, it's 1.0. That means it is a very good model. And this is a very common error that you will say, okay, it's F1 score, accuracy, precision, everything is 1. So that means we have a very good model. No, you need to interpret whether you are getting the thing right or wrong. So you can do kind of plotting and everything there. So that's where interpretation of model or the inspection API comes into the picture. So now let's interpret our model. So interpretation of model is done using the inspection API, which has this permutation importance and partial dependence plot. So permutation importance just gives us the best features after training the model, and partial dependence plots basically plot those things. And these all things we will be covering later on. So first of all, we need to import our permutation importance and partial display from inspection API, and both them live in the inspection API itself. So you can either do this or you can use this, this, since both are from the same API, so we can directly do this. Now, after that, we will need to import our matplotlib because this partial dependence plot display, this will be requiring matplotlib, and we are importing matplotlib.pyplot as PLT. After that, we need to use tree-based algorithms to get our feature importance after training our model. So it is kind of an estimator again, okay? And this we can get from the ensemble module, which I have not covered in the theory, but you should know that ensemble basically means building a model on top of a model, and we will be covering all those things later on. After that, we need to get the permutation importance by providing estimator or test set. So the permutation importance we can directly pass in our test set. And again, by default, it will take a estimator, which is our best model. That is the best model with C is equal to 0.1. Then our X test, which is our testing features. Y test, which is our testing labels. How many times we have to repeat? 10 times. What is the random state? 42. And how many jobs we are doing to use? N is equal to 2. That means it will be using 2 CUDA codes. Okay. And now if I do feature importance printing, that is print feature importance, result.importance mean, here you will find that we are getting the mean of the result. So only 2 features, as we have seen earlier also in our select k-based, we have our 2 features, even though we are passing X test and Y test. And you can see that the mean for both the data set is very close, 4.83, 4.8. So these are the things that you need to be aware about. And the reason we are taking mean is that it kinds of averages out everything. After that, we are going to plot our data. And to plot our data, we will use random forest classifier and the partial dependence plot. First of all, we are creating an instance of random forest classifier. After that, we are going to fit our training data and training labels. After that, we are going to create a display variable. We will be using partial display from estimator, and estimator will be nothing but our random forest. After that, we will passing it our X test, which will be our testing data, and then features, what all features we are using. And here we are not using the 0 and 1. It is actually the index of column 0 and index of column 1, because we are using only 2 columns, as you can see, right? And then we are so obviously you might run into some errors, and here you can see that it says target must be specified for multi-class. Okay, so I figured out the error. The error was nothing but that since our data is a multi-class classification problem, we have to specify the target. For this, I am setting the target class as equal to 0, and here we have to specify this parameter called target as target class. So it will be nothing but 0. You can also set 0 here also, no problem with that. And now if I plot it, you can see that it will be giving us a PPD, a partial dependence plot, and it will just show you how features are related to labels. So all the things that are being shown here, 0.2, 0.4, 0.5, 0.6, is nothing but the probability. So we have our labels -1, 0, and 1. So 0 means neutral, 1 means positively correlated, and -1 means negatively correlated. And you can see that both have similar kind of relationship, that they are negatively correlated. Also, there is a steep drop, that means that it is negatively correlated. So these are kind of things that you can do. Obviously, this is not a very cut model, but this will give you an idea of how to implement things and how Sklearn kinds of make our life very easier. Now, it's time to summarize what all things that we have seen till now and how it works into the entire pipeline process. So first we had this Sklearn.dataset through which we loaded our iris dataset. Then we have our pre-processing where we did our standard scaling. Obviously, we didn't do our max scaling, normalization, binarization because that was not needed on this particular dataset. Sklearn.impute basically to fill the missing values. We created our missing values for the first data point and then we imputed it. After that, we had our feature selection, which gave us the top 2 features that we need to understand. After that, we had our linear model, which was a logistic regression on multiple models. More than that, you can always look at the documentation. After that, we had this tree-based models where we used random forest classifier for identifying if there is a partial dependence on the dataset or not. Then we had this SVM, support vector machines, but again, we didn't use it with our datasets. After that, we created our multi-class output. And for that, we used Sklearn.multiclass and multi-output. After that, we used Sklearn.cluster for algorithm clustering to get if they are cluster dependence or not. After that, Sklearn.metrics to understand the precision score, recall score, and F1 score to understand whether our model is performing good or bad. And we found out that this particular model that we built was, even though showing a very good F1 score, but may tend to overfit. Okay. After that, we looked at model selection, which model we need to use. And for that, we are using trend test express, cross validation score, and its husband found that logistic regression with cross CV is equal to 0.1 will be a very good fit. After that, we had this inspection module on how our feature was dependent, and we found that there was a negative dependence in that. So this example code integrates each specified component in a cohesive pipeline, connecting each step logically in our ML workflow. So lastly, I would like to only share you that subscribe to this channel if you want content from it, and share it if you found this video very useful. And after that, if you had any issues, please comment it down in the description, else I will not know what is your issue. So guys, that's it for this particular video. I hope that you enjoyed a lot while learning all these things, and all the resources will be provided in the description. From the next video onwards, we are going to look at individual component in a great detail, and I hope that you will like that too. Do share your thoughts and comments. See ya. Till then, bye-bye.